maybe it can be done without waiting until next system, just right for this model that you're working with. Okay, yeah, now I understand. Thank you.
And then same thing, I already had these figures laying around, so I just, copy pasted it in here. But, if we have more than two orbitals or states, then we could have, something like this where it might be sort of a cascading effect where it, kind of evenly shifts from one state to the other. Or, maybe we get some weird effects going on where it kind of, if we have like a 3-state system, for instance, maybe like the ground state and the second excited state get more populated, and then the first excited state gets depressed or whatever. There might be some interesting dynamics to capture in figures similar to these.
Okay. Let me quickly type. So the quantum states of the field of this oscillator that represents laser cavity degrees of freedom, it has several quantum states, and then they can be populated or depopulated as we go through the time.
Yep. Yes. Yeah. So this should also work for the photons as well as electrons. Once we
exactly.
because if we only have two states, it's trivial. You know what I mean? If it's not in one, it's in the other. But once we have more than that, then this might actually show something.
So if you are using this style of figures for photon, then we do not need to wait many electrons. Right. So same style, but not for electronic degrees of freedom, but for different quantum states of photonic degree of freedom.
Yes.
Because next system will be in the next paper. It's not realistic to process several models in one paper. It will be a thesis rather than a paper.
Yeah. Well, I'm going to need one of those eventually anyway. So.
Yeah. Okay.
Those were just like the templates for my hand-drawn little graph. Okay. So I had some extras.
Yeah, it's very generic. One can fit there anything. Okay. Are there more questions to London, or criticism, or admiration? Okay, please join me thanking London. And we have one more work. So here are PDFs and comments, but maybe before going over the comments, Amir, what do you think about sharing screen and showing it as presentation?
Yeah, sure.
Let me check if you have this. Yeah, you are co-host.
Okay, I will finish it very soon. So. Can see my screen?
Mm-hmm.
Yeah, so this work was partial, part of it could be morphology and gas transition temperature. We are working on that for a force field calculation paper. But the other part could be charge transfer in photovoltaics, donor acceptor polymers that we had a poster in Sanibel about that. And also submitted a paper. The only difference is here that we are trying to make some condensed 3D amorphous systems to take a look through the charge transfer of those systems. So the polymers here that we are looking are PM6 and PM7. These are kind of most brand new and high performance conjugated polymer that are being utilized in organic photovoltaics. There are two questions here. First, Dr. Killen asked about what is a strong storage modulus. Sorry, I was lazy. I just take a screenshot from our submitted paper. It's a modulus that people in experiment calculate over the range of temperature to find some peak in the change of temperature, and those peaks represent the glass transition temperature of the polymer. It's in the DMA test. So this is not related to our research. I just put the last second a snapshot of that paper to have the chemical structure. So beside that, PM6 and PTB7, the most brand new acceptor unit is Y6 here. So I replaced the ITIC from previous work with Y6 from Y family acceptor units. And today, the PM6 Y6 blend is a state of the art in the organic photovoltaics. So it could be very interesting to take a look through the first principle calculation to how charge transfer looks like between these systems, PM6, Y6, PTB7, Y6, and to have a better comparison, I still want to keep the PCBM acceptor to take a look through the difference between fluorine and non-fluorine acceptors. And also that was asked that what is OPVs? It's organic photovoltaics. And how we generate the models. So to have a balanced system, I just generate a 3 monomer polymer chain, get it to the equilibrium situation, also equilibrated structure of the acceptor unit. Then with the MATLAB code, I pack the system. For instance, I put 2 polymer chain first, because we need to have a 1-to-1 weight ratio, then calculate the needed weight for the acceptor unit and pack it there, then run the simulation for around 20 nanoseconds to get to the equilibrium position. I will come back again to your question, Dr. Killen, after that. And then also we convert the equilibrated snapshot at the end of the simulation to the postcard file. And at the end, we need to run the ground state calculations and ab initio calculation based on those. So Yulan, I think, asked about how we change the format to the postcard file. So I had the output file of the equilibration. I had XYZ and type of the atoms. Then I wrote a code to convert it into the XYZ, and then on the photon, convert XYZ into the postcard file. The important point is that at the end of the equilibration at the room temperature, I had the equilibrated size of the simulation box. So that size will give you the equilibrated density. Pronouncing this word is killing. And that size should be implemented in the postcard as the equilibration dimension. So that was the main purpose of running for molecular dynamics. So how I perform temperature and pressure, yeah, that was around 20 nanosecond. I use multiple isobaric and isochoric, if I'm pronouncing them right, ensembles. Yes, at the end, I run on under NPT ensemble. I let it to go to the equilibrium situation under at the beginning, huge pressure and temperature with annealing, then cooling down and get rid of the pressure and temperature. But at the end, that was relaxed under the atmosphere pressure and reached to the room temperature. We will come back to some results you ask, and I just write few line codes to take a look through the density and energy during the equilibration in the force field calculations. Here is I just showed them in a different color, 2 chains and some acceptor units. So at the beginning, I just gave the system a density of 0.7, then we have a calculated size for the simulation box. So at the beginning, we have just a fixed boundary condition under NVT ensemble, where the volume is a constant, to let de-overlap the atoms and help it to get closer to the equilibration. And Yulan asked, it's not, look, this one is not a periodic boundary condition. It is and it's not. You are right. I generated this file by MATLAB, but when you are using LAMMPS for the force field calculation, it will immediately recognize the boundary and pack everything inside the boundary. So if during the initial configuration something goes beyond the boundary condition, in the first snapshot, it will pack all of them inside the boundary. So it's not a big deal here. And at the end of the simulation at the room temperature and the 1 atmosphere pressure, this is the equilibrated bonds. Yeah, I will use your setting. Dr. Killen, you mentioned use dynamic bound and the VDW setting. I will do that. So here is the 1.3 gram per cubic centimeter equilibrated density, kind of close to the experimental reported values. So this is something that we are going to, actually I already converted it to the postcard and we are running on the Cori to see if we can get to the grounded state calculation. It's pretty large system, maybe around 1500 atoms and 2.2 nanometer bulk size, I think. And yeah, so we have 2 polymer, M6 PTB7. So we are running first pure polymers, also the combination of those polymers with Y6 and PCBM. Overall 6. I don't know, Dr. Kinney, if I need to run pure Y6 and pure PCBM. If you suggest that, we can have them also. I'm not running them yet. And target properties, for some part, we just need to have the grounded state calculation, for instance, absorption spectrum and density of states, for instance. But definitely the final goal would be charge carrier dynamics to see how they looks like in a condensed system. Also, Dr. Killen asked how the density looks like over the force field calculation. So this is, you can see this plot? Yeah, this is the density. Do not panic with this fluctuation. So this is the technique we are using in the equilibration of the polymer. We put a huge pressure and then release the pressure to the 0, then put a lot of pressure again. So this fluctuation is because of that. But as you can see at the end, at the room temperature and atmosphere pressure, there is not that big fluctuation in the results. So this is the plot of the density. Also, I just plotted the energy. So if you take a look through the potential energy, so energy show a big drop after the minimalization and also decreasing the pressure and temperature. And also for the total energy, also the same behavior expected. So based on this area at the end of the simulation, we can say that the generation of the model in the force fields are kind of reliable. However, I think they are still far from the grounded states because they are based on the force field calculations with much lower accuracy. But I hope we can get to the grounded states sooner and then start some dynamic calculations. So that's all plan and results that we have right now. No result, but some plans.
Yeah, thank you, Emir. It's really great, really great.
I try to answer all questions. I don't know if I missed anyone or.
Let's maybe go over. Maybe since you're already sharing screen, you can show.
Yeah, I have them.
Yes.
So, sorry, I cannot pronounce the name maybe correctly. Hadassa, or ask what's organic photovoltaics. So it's what's OPV is organic photovoltaics used in solar cell applications. So Dr. Kinney, we talked about this storage modules for DMA test. How does compression come to this flowchart? Do you compress continuously? I alternatively used NVT and NPT based on our previous experience in the force field calculations. Constant volume at the beginning, yeah, I just keep constant volume to de-overlap the atoms and chains, not entangle into each other.
Mhm.
But at the end, that was under real pressure and temperature. So
Can we stay here for a little
Mhm.
longer? So your mu figures at the very end of presentation look very convincing that the procedure is reliable, but I feel a little discomfort with the words how it is explained. So here in the middle box, you turn force field molecular dynamics for 20 nanoseconds.
Mhm.
So it makes a deceptive impression that you continuously run molecular dynamics without changing parameters. And it looks like you are changing it's not a continuous 20 nanoseconds run. It is a sequence of NPT and NVT ensembles, which is different from what is said here in this box.
Yes, the language is not correct that way. Yes.
Okay, so maybe when you do it next time on the conference or in the paper, you will improve it. And another question, there is no trap, I'm just trying to understand.
Mhm.
Your mu figures show that energy is convergent.
Mhm.
Like all characteristics are convergent, but what is happening with energy, with conservation of energy? Does energy is conserved during your molecular dynamics just by settings you're using, or there is a way to lead energy, especially kinetic energy, out of the system?
It's a good question. No, I think the second is not the case here, the second statement. So I think in force field molecular dynamics, the system is trying to adjust its volume and its temperature based on the Boltzmann equation. So when you have a larger energy in the system, kinetic, it will increase the temperature of the system and non-bonding interaction in the system, and at the end try to affect the, I'm not 100% sure this is the correct or no, but interatomic distances at the end will change the volume of the system. So when the system has a higher energy and you release the boundaries to fluctuate, it will try to adjust itself by changing the boundary. Or for instance, if you are running under NPT ensemble, you can say that, okay, the pressure is constant, temperature is constant, and then a number of atoms also is constant, but you are free to change the volume. So then it will convert it by the change of the geometry of the simulation parts. On the other hand, if you run for NVT, you will force the system go under the fixed volume, fixed temperature, but the pressure could be different. So that energy will convert to the internal change in the internal pressure of the system, and the pressure changing the pressure tensor of the system. So yeah, we do not have any interaction with the environment around the parks. So I don't know. I made it more complex, or
No. I'm developing a clear picture. I'm going to summarize what I understood, and then I'll ask London to help with terminology, and maybe Hadassah as well, as two trained physicists in the audience. So when we are doing thermodynamics with like rod and piston and some gas inside, if we put the system on a in the ice bath, it means we are keeping the same temperature. But it, right?
Mhm.
Ice bath, melting ice, which means temperature inside this system will be constant.
Mhm.
Are
But-
we imagining like a continuous heat source at that point though? Or are we imagining,
not-
it's like, I'm thinking like a car engine when you're talking about like a rod and a piston, like I'm, you know what I mean? Like
Exactly.
explosion, explosion, explosion.
Yes, but let's look for only one little portion of this cycle.
Okay.
When it cools down, when it like due to the radiator cycle, the temperature, the heat is let out from the rod and piston, which means we intend to keep temperature the same, but the kinetic energy is continuously decreased through this through our effort to keep temperature, and this gives us a opportunity to go from higher energy to low energy in the overall configuration.
Mhm.
So here is the question: what would be the smart words from the thermodynamics to describe this person, like or whoever was taking thermodynamics recently? Maybe David can help as well. So the thermodynamic system under constant temperature is not a closed system. The energy is allowed to be released. And through this mechanism, we can arrive to a minimum of energy. Would it be correct to say this way?
I think so.
So
So we are doing something. We are jamming the system with pressure. We like keep or release constant volume, keep or release constant pressure, keep or release constant temperature, and as the result, Amir is showing that we are arriving to a minimum of energy, or one of the local minimum, but it definitely total energy decreases. So even if we have no acquaintance with thermodynamics, it means the system was open. The energy was released from the system to outside.
how? So I would say
for-
under NPT ensemble by changing the volume,
Mhm.
right?
So while explaining your procedure to outsiders, you should find like correct academic words to explain this process.
Yeah,
That,
okay.
why system is arriving to minimum of energy, why system is open, how the energy is leaving. And it's not for right now, it's for the future. Okay,
I got your point. Let me, so it comes from where you define the, let me, if I can write anything. For instance, the non-bonding interaction, how do you define the, for instance, energy, and this is the, I have a horrible handwriting by mouse, and anyway, but by mouse is much more worse. So if it's the distance between, R is distance between the two atoms. So the system would be try to reach out to the minimum energy of the non-bond interaction at here. So this function, for instance, that 12.6 Lagrange potential is defined for non-bond interaction. So other force field parameter also, for instance, bonded potentials follow almost the same behavior in the system. So when we run the simulation under the time step over the time by in the molecular dynamics, we will tell the system, okay, this is the equilibrium situation. Then when for instance, we define the equilibrium bound length. When it's stretching, it knows that it should come back to the equilibrium state. Or when it's squeezed, it will try to repulse the atoms to reach the equilibrium situation. The same happens between the two different atoms in two different chains, for example, of the polymer through the non-bonded interaction to reach to this area. So this changing in the geometry tends to go to the lowest situation of the energy.
Yes, but you're not doing optimization, you're doing molecular dynamics.
Yes, but molecular dynamics
there is a kinetic energy. As soon as you contract or expand bond lengths, the potential energy is converted into kinetic. And then there should be a mechanism to dump this kinetic energy somewhere.
I would say that changing between the free volume inside the system and interatomic distances would be exchange in the change of the overall volume of the system and will dump the energy. But in the thermomechanic terms, I'm not that good. I can take a look for the next time to have a better discussion on this.
Okay.
Anybody else, if you want to put a comment, I would be happy.
So it's our little motivation to refocus on thermodynamics. And probably it is most active for Steven, who is taking this course right now.
This is the most maybe difficult and as well as easiest question that I ever faced in this force field calculation. It's very difficult to answer. I completely understand that, but I cannot explain that. I don't know. But yeah, I will definitely review some thermodynamic concepts. We will discuss it next week or next 2 weeks.
Okay. Okay. Sorry for interrupting. Let's keep going through.
Yeah, no problem.
Where we stopped.
I cannot clean them. Yulan asked, does it look like a periodic structure? We already talked about it. Then how did you convert the structure from force field snapshot into periodic structure using VASP? So it's just a simple way that we use based on those 4-track codes Dr. Kilin provided. For me, I just saved the last snapshot, this snapshot as an XYZ file. LAMS cannot do that. I just save it in the LAMS format, then write the code to convert that to the XYZ. Was not that difficult. You just need to know the atom type and give it a letter and also have just the coordinate. Then we had that file there. If somebody is interested, I can share that code. And just a suggestion, sure, I will take a look. How to trust the model, we already discussed that based on the equilibrated density and also energy of the system at the end. Yeah, that's all. So is there any question in the chat now? No.
Okay, please join me in thanking Amir for a very interesting story and interesting discussion. So,
thank you.
More questions? Okay, I think
I have a question from you. For such that amorphous system, how clear would be the exploratory charge dynamics over time?
It is fine. If there are more than one donor and more than one acceptor, it will be a little problematic to make this space migration diagrams. But for energy migration, it will be not a problem at all. And it will go very close to the concept of disorder. So in the true ensemble, the each donor and each acceptor will have slightly modified energies because of the different spatial arrangements, because of the different phase of fluctuations, different distances, and in average, one just needs to take into account all possible donors and all possible acceptors, which have typically we take into account into the line width, line broadening in like density of states and absorption, and we can do it in other observables as well. So it goes very nicely along with concept of disorder. Disorder in a sense of distribution of energies, again, energies along the average value. So this one snapshot of amorphous structure doesn't look like a philosophical challenge. The results for this one snapshot are expected to be a good representative case study for the whole system. And it definitely is much better than isolated single donor and single acceptor. Okay, so next week, if you are not traveling, not celebrating spring break, we will meet to discuss details of London's project. If there will be more volunteers to present, everyone is welcome. And in 2 weeks, please, if possible, try to prepare updates of what was presented today, and more participants with more drafts of papers are very welcome. So anything we need to announce right now? If no, then adjourn is announced, meeting is done. Everyone is welcome to disconnect. And I think we need to talk with Amir, Sarah, and Kea, but if anyone else wants to talk like past the formal adjourn, please stay on the link. And if you think you are done, feel free to disconnect.
I do have one question to bring up. At Svetlana's group meeting 1 or 2 weeks ago, Stefan, the Dr. Vasilov student, mentioned making some changes to modernize Photon.
Mm-hmm.
So I spoke with him about that today, and he said that he would want to, for me and him, to meet with you and Svetlana to discuss the exact details of what exactly we need to keep in mind for functionality when making that upgrade.
Okay, do you have an estimate how long this meeting should be? Is it like 15 minutes at the end of the Friday's group meeting, or we should like assign 2 hours and meet in person?
I can talk with him about that, but he said the soonest that he actually would be available would be next Monday.
Okay.
And I think it might not take more than an hour.
I'm willing to contribute and willing to join, but let's talk to all parties. Yeah, thank you for bringing it up.
Then I guess I have an update for you, Dimitri.
Yes.
So I talked to Friedrich, the like the head of the math department, and he was saying that for me to not TA, you know, going forward should be totally fine. I mean, I'll have to finish out this semester still, but like after that, I mean, as long as the funding is all secure and everything, like that shouldn't be a problem on the math side of things. So
Okay, but
we should be good to go.
He doesn't encourage to stop in the middle. He wants
No, yeah,
to
that would be very problematic for Calc 2.
Okay.
But yeah, so I just need to talk to Indranil Sen Gupta at this point, and then after that, everything should be squared away, and we should be good to proceed, you know, in the future.
Okay, yeah, sounds good.
That's all I got.
Yeah, thank
Have a
you.
good night, everybody.
Yeah, good night, London. Yun, do we need to talk after we are done with Amir, Sarah, and Kea?
Not really. Is there any feedback from the 6.5 content tube from the collaborator?
What do you mean 6.5?
Oh, no, the 11.0. I'm
Oh,
sorry.
no. Let me maybe stop recording and